I've given her an introduction already, so the stage is yours.
Yep. Can you hear me? Okay, so welcome everyone. Today I'll be talking about how to write debuggable TensorFlow code and going further, how to verify your TensorFlow code. My name is Wei. I work at Prowler, a Cambridge-based research lab company. My focus at Prowler is to use machine learning to train algo-trading algorithms to trade stocks and futures. In order to do that, we write a lot of TensorFlow models, and we have to say TensorFlow is very powerful, but the code is very difficult to write and very difficult to understand and to maintain. I'm sure that some of you have the same experience. And what I mean by that, so in order to understand and debug your TensorFlow code, you need to evaluate tensor values, but those tensor is a multi-dimensional arrays. So the data I'm working on is 5-dimensional arrays. It's 2 more dimensional than the most dimension that I can see. So there is a problem. And also, TensorFlow is graph computation. So to understand, to make sure that your graph is actually wired correctly is very crucial. The de facto way to do it is to use the TensorBoard visualization. But once you open the TensorBoard visualization, you will be overwhelmed. The chart there consists of hundreds of nodes and edges. It's not for human. So, and also the tons of tips of how to write better TensorFlow code around the internet. But you never know how many should you implement. And even if you implement a lot of them, you have no idea if your code is correct. So those problems prevented me from sleeping every day for quite a while. During the night, it's actually okay. So, eventually it occurred to me why it's difficult to debug TensorFlow code, because we haven't told the debugger what we mean by the code being correct. So we need to have specifications for that. So specification defines what is the code is supposed to do, and your implementation describes how to actually do it. Now, I have to make clear that specifications define the correctness with respect to the algorithm, usually from a research paper. It does not describe whether your code can learn a meaningful model. That is dealt with by standard machine learning practices, like for example, plotting the loss curve in training and testing, doing cross-validation. And right, so in order to effectively debug your TensorFlow code, you need to have specifications. But we know specifications, writing down specifications is very difficult. And at Prowler, we developed 3 specification writing techniques and the software engineering process to apply those techniques. So I'll introduce each of them in this talk. The first one is tensor shape assertions. They validate the shapes of your tensors. And the second one is called tensor dependency assertions. They validate your TensorFlow graph structure. And the last one is called tensor equation evaluation. They validate your numerical calculation in all the equations in your algorithm. So let's start with the simplest one, shape assertions. Well, you write TensorFlow code, you introduce tensors. This technique requires you to write an assert to check the shape of every tensor you introduce. For example, in a typical regression setting, you have a prediction tensor, you have a target tensor, and you have a loss tensor. The loss tensor is the mean square error between your target and your prediction. Now I added 3 assertions checking the shape of those things. It sounds like super trivial, but once you start writing those things, oh boy, you realize how often you're wrong about those assumptions of the shapes. And the TensorFlow broadcasting mechanism. You're just going to hide all these problems and make sure and pretend the code is going to work. It doesn't. Okay. Now we finished the first step. It's actually very doable. Imagine actually you sitting there every day writing this assertion. It's doable. So we move to the second stage. Now we want to make sure your tensor graph is wide correctly. That's very crucial. All right? And if you do a TensorBoard visualization, this is what you see. I don't even know how to start. It's too complicated. However, the insight here is that usually you're only interested in the tensors that you introduce. And you only need to verify the relationship, the dependency relationship among all these tensors. By dependency, I mean if the value or evaluation of tensor A depends on tensor B and C, you should see edges in your tensor graph. And note that in here, you are thinking about validating the structure of the graph. You are not thinking about validating the numerical calculation. For example, I can have tensor A depends on tensor B in A equals to B plus 1 or A equals B minus 1. You don't care about the numerical operators here. You only care about the dependency here. That makes it easier, much, much easier. So, well, it's a lot easier, but you still need a piece of software to do it for you. So we developed a Python package called TensorGroup Dependency. What you do is you create the TensorGroup Dependency, and you add the tensors in your tensor graph. You only add the tensors that you want to visualize. You give them a more readable name in the representation, and you call general dot representation. Dot representation is a graph description language which facilitates visualization. You print it, and you can visualize it easily. So here is a much simpler part of your TensorFlow graph describing the dependency among those prediction, target, and loss tensors that you introduced, you created. Let's see what the graph means. Every node represents a set of tensors. A set of tensors meaning usually you want to visualize a set of TensorFlow variables together. For example, you want to put all variables in a neural network in one node. The reason is if you're using TensorFlow's API to create neural networks, the chances that you introduce bugs there are very slim. You don't need to care about the internal layers. And dependencies are indicated with direct edges. So obviously our loss tensor depends on our targeted prediction. And the graph also shows the shape of the tensor. So you have an overview of all the shapes and how they flow and how they transform. And your job here, by looking at this, is to ask yourself why every edge exists. Because an edge exists because you wired up the tensor graph like this. Does this wiring match what you think your algorithm should do? So you have to explain the existence of everything. Not being able to do so for an edge usually signifies a bug. And this is by using this visualization and asking you a bounded number of questions can help you quickly verify the graph structure. Now, suppose you've done all the question answering. Now you need some concrete things you need specifications to certify that this is the graph I want. So you call another method from this package, generate assertions. And these are the assertions generated for you, certifying the chart, the dependency relation that you just verified in your brain. Now you put these assertions in your code, it is checked automatically for all future executions. This is all done automatically. And now, the previous chart I showed is a toy example, and here I'm showing an actual generalization for the TD lambda critic. It's a commonly used machine learning model in the field of deep reinforcement learning. So this is the actual graph, no more, no less. So you immediately see that it's very manageable, it's understandable. So a bunch of tensors, each one of them you write your own code to introduce, and all their shapes and all their dependencies. Now, usually in a machine learning application, you compose different learning modules together. So here, this is a chart for another critic called Generalized Advantage Estimation. So this critic uses the TD lambda critics before. So the TD lambda critic is actually in here and here, which provides some inputs to this critic. And the graph is smaller. And finally, this is the whole chart for the code for DeepMind StarCraft 2 learn. And it's way smaller. And it uses the previous two algorithms. So this is a very nice property when you can control which nodes to verify and check and verify and visualize by just writing code against it. And because of this composability, the verification effort is smaller if you move into higher and higher level of your model composition. All right, so this package is actually a key component in the whole process, and with it, the whole process is practical. I'll explain why a bit later. At Prowler, we're in the process of open sourcing this key component. If you're interested, drop me an email, and I'll let you know when it is ready. Let's continue to the last technique. Now that you verified your shape, you verified your graph structure, you have to verify your numerical computation. A equals B plus 1, not B minus 1. You have to do that. So the way to do it is that take an algorithm from a research paper. You've already written the TensorFlow code for every equation from this algorithm anyway. Now, you need to write assertion to check the numerical values from the calculation of each of the equation. How to do that? You do it after each optimization step. Usually in your optimization step, you have a single call to TensorFlow session.run. It's a single call because multiple calls will cause problems and will slow down the training process dramatically. Usually you do a session run over the operations to update your model parameter. Now, include all the tensors that you need for your equations, for every equation in your algorithm. Once you get it, so here I put my prediction tensor, my target tensor, my loss tensor. Now, after session.run, I have those values. TensorFlow gives those values to you. So you write the same equation, this time in NumPy language. So in NumPy language, mean square error equals to the mean over the difference of your target and prediction squared. The advantage of writing it in NumPy language is that it's much, much simpler than in TensorFlow. And you can write loops, you can write whatever things here to check the numerical correctness. It's not like TensorFlow, you need to deal with many, many dimensions and all these crazy things that it's not, obviously I don't like them. So I couldn't even find a proper adjective to describe it. But in Python, we're free. So you write assert almost equal. That's it. You do it for every of your equations, roughly a dozen. And yeah, and we apply those techniques on all these learners that we wrote. And so here is the the number of hours we spent writing those learners. Actually, we wrote it very fast. I'm very familiar with writing those things. And here is the debugging time we spent. That's the column I want you to focus on. Debugging time means the time we spent in writing down those assertions, running the codes through some test infrastructure, random test generator, and observing the assertion violations and fixing the problems. By the way, when there is an assertion violation, it does not necessarily mean your code, your implementation is wrong. The specification can be also wrong both. In our daily life, roughly 50% of the case, the specification is wrong. But the important point is that the difference, the discrepancy between these two, guides you towards verification. And we spend 20% more time. This is really a wow factor. We used to spend weeks validating those algorithms. At the end, we still don't know if the code is correct. Now we know. With only 20% effort, we know the code is correct with respect to the paper definition. That's a much, much stronger requirement. And also, we break down the time and bugs we found by applying each of the techniques. For example, shape assertion, trivial to write, where you find many, many bugs. And finding bugs in early stages help you a lot in finding bugs in later stages. So it's, I'm quite surprised to see these numbers. And yeah. Now, I hope I at least partially convinced you that those assertion writing techniques is effective. Now let's step back and think why. First, the whole process is practical, so normal software engineers, normal data scientists can afford writing them down. All these three techniques are very practical. And second, they provide fault localization. This is actually the key part here. Locating a TensorFlow bug is very difficult. Locating and finding out the origin of the bug is very difficult. Now, if you apply those assertion techniques in order, they help you. For example, if you have an assertion violation in TensorGroup Dependency, you know your tensors are correctly shaped. And if you have an assertion violation in your tensor equation evaluation, you know your tensors are wired correctly. So the only problem you have is the numerical operators or the parameters that you provide. So every time you have a problem, your focus is very, very small. So you can effectively locate the problem. And so the reason, it is actually because of fault localization means that the TensorGroup Dependency package is crucial. We actually developed the third technique first, tensor equation, because that's obvious what you have to do. Everything else is auxiliary. But when we try to do this, we try to only write down the tensor equation evaluation. We found fault localization is very difficult because you have a problem in your numerical calculation. You don't know where to look for the problem. Now we get back to add the necessary pieces, so the whole process becomes much painless. That's why I highly suggest you apply those techniques in order. They are there for a reason. I spent months finding out the reason. So, and also the last thing is that it's an engineering process. You know exactly what to do in each stage. And there are finite, all the steps are bounded by the number of tensors and equations in your algorithm, usually in a dozen. So it's manageable. And don't overlook the fact that it's an engineering process. When people know the exact steps to do, they're just much more efficient. That's, yeah. Okay, so With those assertions, we have additional benefits in advanced testing. If we think about what a test consists of, two parts, constructing the input and constructing the output. Now, we are lucky when we're doing machine learning code because everything is number. You can easily generate all matrices with different properties. It's not like we're dealing with file system. So think about how do I write an assertion saying the file is read correctly line by line. It's very difficult. How do I write an assertion to assert that my email is successfully delivered? But in machine learning code, you generate matrices. That's your input. Now we already have the articles. That's the specifications. We already wrote them down. So advanced test generators can be easily implemented. This is what we are using. So you generate inputs in different corner cases. You run them and see if the test, the code reviews some problems. With this, you can easily test things that you need to spend months to do. Okay, so in conclusion, TensorFlow debugging is difficult because of the lack of specification. We developed a way to write specifications to verify the correctness of your TensorFlow code with respect to the paper definition. We proved that the whole process is very doable and effective. And we are open sourcing one of the key, the only key component that we developed. And if you're interested, let me know. And with that, I'm happy to take questions. Thank you.
That was very powerful stuff. I think we've got a new challenger for most views on our YouTube channel. I think people are going to come back and revisit that content. Do we have any questions for? Yes.
Yeah, I'm Zach Eaton Rosen, I work at UCL. You attribute some of the difficulty to TensorFlow itself. So the obvious question is, what about other frameworks?
Actually, TensorFlow is part of the problem because TensorFlow does this graph computation. It's in a way in a normal Python, which is imperative. So then you have this paradigm conflicts all the time. That's why we usually find writing TensorFlow code more difficult. Well, unless you have PhD training in writing state machine-based computation, then it becomes natural to you, but not for everybody. That's why you have these problems. But numerical calculation, all this graph computation does make testing simple if you know the right way to do it. Yeah. The reason behind it is that you can think of it as side effect free. So it's more functional in a way. Testing functional code is much, much easier than testing imperative code. Yeah, that's why the whole process, including writing specifications, actually works. Normal software verification of imperative code is difficult because of the frame problem. You write down something, actually you change some other things. In TensorFlow, this is minimized. Only occurs when you're pointing two tensors together, pointing two names to the same tensor, but you're not using the name. TensorFlow doesn't care about which names you associate with the variable. It's just that variable. Yeah. Yes. Yeah.
Hi, Jakob Langer, Modana. So thank you so much. This is wonderful, and it solves so many of the problems that I have had with TensorFlow. The real, it's a real pain. So I have two quick questions. So one is, how does the introduction of TensorFlow Eager change any of that? Because that's since 1.7, I believe. And then the second thing I wanted to ask quickly is, so there are some more advanced architectures like generative adversarial networks where generating those dependencies can be a bit more difficult because you then have different scopes and different 2 to 6 different networks. So does the TensorGroup Dependency handle that as well?
first question is easy. I don't know about it, so. Second question, it does. We write plans all the time, and the key point of using TensorGroup Dependency is that you don't care about the namespaces, because we designed it that way, because usually you want to apply this after the fact. Now your namespaces are already tricky in the first place. You don't want to touch that, but you only put tensors in it, or tensor groups in it, and in TensorFlow tensors are hashable, so they have an ID. So as long think about the guns, what you did is you're linking output of a network to input of another network. So that will be a tensor going into another network. So you handle exactly the same way as a single, say, a regression case. There is no difference, and we do find verifying the structured parameters of guns. Well, it doesn't signify as a problem to us. Yeah.
Yes.
And it's a great start. Basically, you're rediscovering unit testing for deep learning.
Yeah, and it turns out it's very easy.
Yeah, and that's expected. Have you considered using any of the unit testing frameworks, libraries?
We wrote our own. So once you have the model in, writing a unit test framework is actually trivial. Well, the non-trivial part is how
Getting the capability to write an assertion, yes?
Yeah.
Okay, thank you.
So that part needs a bit of thinking. The difficulty is how do you generate different inputs, generate a single input for an input subdomain. So then you have the minimum number of test cases, because one test case run can be long. It can take 2 hours.
Yeah.
So
So do you create mock objects?
we don't, because as I said, it's just matrices, so there's no need for mocking.
Okay,
Yeah.
very good, thank you.
Any more questions? Yes.
I was wondering if you thought about kind of using a kind of functional approach so that all of your assertions were kind of hidden, so that you just write code naturally and get all of that thrown in free.
Yeah, you write code naturally, but you still need to tell the debugger what's the correctness of your code. What do you mean by correctness? Is it sorting algorithm or is it regression?
Another approach is, for example, if you're using a wrapper like Keras. Keras will do all of those kind of assertion tests to make sure that the tensor dimensions
Or
fit.
PyTorch.
Yes.
Or PyTorch.
So what's the advantage of your approach versus using a high-level wrapper library?
I use both, and I write assertions for both. So that you call the Keras API to generate guides, to generate neural networks, but it does not tell you. Well, let's say you need to. We are doing machine learning algorithm research, so our job is not to call off-the-shelf algorithm. Our job is to invent one off-the-shelf algorithm. So in there, you're in a free space where you can make a lot of mistakes. That's where I need it.
Okay.
Yeah.
Well, overall, it's just a very good engineering practice. In classical software development houses, your code would not even deserve to be an alpha if it doesn't have unit and coverage tests. That's it.
Right. Yeah. Yes.
So, great talk, thank you. With debugging, often you know the unexpected results that a program is outputting, so you know what you're looking for, and you can debug it. How often, as you went deeper into the 3 different types of assertion and strategy, did you find that you were able to discover new bugs that were not visible at the start?
Yeah, so here, what this process gives you is a way of discovering all bugs. Compared to previous experience, you're sitting there, you don't know where to start, and you observe your machine learning model doesn't learn. You don't know why, and where do you check? Is it my tensor? Is it my structure? Is it my numeric calculation? So I sat down and analyzed. Well, first I wrote down like 50 bugs I found, wrote down each of them, and analyzed the process, how I found them, and then put them into categories. So how do I find them easily in a more mechanical way? And that's the well, I have a lot more stages which are optimized away. So these are the current best things I have to offer. Yeah. It's a process to find bugs. You don't have question of how do I start, where to look. You follow them. That's why it's an engineering process, and it's very easy to use and it's very powerful. So you know what to do, which is a great starting point. Yeah.
Yes, at the back.
Do you see any audit opportunities?
I'm sorry?
Do you see any audit opportunities?
Any
Audit opportunities?
audit? What does that mean?
Check that other people's code is running as it says, and perhaps they will challenge the decision made by the groups.
So we're currently applying these techniques at Prowler, and we are requiring every machine learning module to have these assertions. So we organize the assertions into a correctness validator. So you have to have it to ship code to the customer. Well, otherwise, it's very dangerous. Take papers published in top machine learning conferences. When you actually sit down and implementing them, many of them are wrong. That was simply, yeah. So you need to be very careful about the correctness. You have to, because the dramatic impact. For example, I'm writing software for automated trading. If my code works very well because of a bug, then so that's why you absolutely need the notion of correctness here. Yes.
We know that you're building a strong team at Prowler. You have built a strong team at Prowler. How much has the application of these assertion techniques changed your hiring criteria?
You're welcome to send CV in. Not knowing this is not a problem. We have a process to introduce you to the assertion writing code issue and thing. But I'll say it's an education task that you need to somehow change the mindset of people. It's very rare that a data scientist can arrive with the right set of correctness notion. It's very rare. You don't see that many to come along. But that's why you need an engineering process. It's not an art. You need a reproducible process and effective result. And with those results, people will change. And this will be slow. Writing assertions is not that hard. It takes 20% time, but it saves you 100% of time later on. Yeah. Well, we'll see.
Yes.
Yes. Two questions. One, we would appreciate if you could put your slides up
We will do that. Yeah.
on the meetup so we can get a copy. The second one is, what about the question, because traceability and reproducibility are very important, but we are finding that, for example, Python libraries, as it goes from version to version, could create a difference.
Yes.
When you use your training, you use GPU for your training, and then the application is running on TensorFlow Lite, it actually completely produces a very different answer. So how do we make sure that there's a consistency on the model created by TensorFlow running on a GPU with where it is applied, because then you have a completely different world or answers that you produce.
I have this nightmare.
That keeps you awake.
I don't know the solution yet. Yeah, we run into this exact problem all the time. Yeah. Throw me an email. I don't know what to
But
say.
the problem is the world is already doing this in production. But they are not reproducible. There's a lot of fake news out there being produced by AI.
So what we do is that we have to run the exact stack, exact TensorFlow version, exact GPU model, exact CPU
And
in
in this
production.
situation where they fix a Python library, so the original training data is no longer actually producing the same results.
Yeah. Yeah. Well, even
So how do you notify that, hey, wait a minute, you have to recall all your applications?
we have automated general tests. They run well. They run all the time. Some of them take hours to run. So if a regression happens, either if all the assertions are still passing. Oh, by the way, running the assertion are expensive. It slows down your TensorFlow code, say, by 100%. In production, you run with Python minus big O. Minus big O means run without assertion, without optimization. And so you have, it's much faster. Then we have all this loss plotting in training and testing. So if they are different, we see. But we only see the symptom, we don't find the problem. Then you look at which library you upgraded. Well, the first library to look at is TensorFlow. Because the performance changed dramatically from one. Well, in a good side, But yeah, we are having exactly the problem, but we don't have a good solution for that yet. Maybe it's for next month? Well, we'll see.
On that note, Yi, I think you've earned your beer. Thank you very much.